Hi, my name is Ferdinand Somorowsky and I work for Fraunhofer Institute for Silicate Research, ISC, in Würzburg. And my talk today is about silane-based innovative materials, on the one hand coating materials, on the other particle-based materials. The Fraunhofer ISC is a material development institute with a long history and with a lot of different application fields, starting from bioeconomy up to hydrogen production and also biomedical applications. We really start from the scratch, so material chemistry is in the center of our R&D. We work on multifunctional coatings, on particles, on magnetic materials, but also on application technology, so micro-optics, electronics, specialty glasses, and this is covered by a large analytical and service department. We also take care of biomedical applications, biomedicine, and also high-temperature materials. Develop on smart materials with a sensor or actuating functionalization. My talk today is divided in 4 parts. The one is about Omocere itself, about general aspects. The second about PFAS replacement. The third about bio-based materials and also biodegradable materials. And the end will be particle-based materials, especially nano and superparticles. The Omocere, it stands for Organically Modified Ceramic, is a trademark of Fraunhofer ISC, and it's a wet chemical hybrid polymer coating. We try to combine advantages from the inorganic phase, from inorganic structures, so high inertness, high barrier, high chemical stability, with advantages of the polymeric materials, so flexibility, for example, or good processability. And when we combine it together, we have like a toolbox and adjust and tailor-made the properties of the materials. So the Omocere is not one material, one formulation, it's really more like a material class and the potential to adjust and optimize the property in a huge range of materials. What is Omocere itself? A little bit in the chemistry, we use such bifunctional silanes. So all of the silanes has this blue box, cellulose groups, and they will be processed by salt shell chemistry, so hydrolysis and condensation, and the other parts are more organic. So here we can integrate functional groups, so also network formers, and Omocere consists of several of these silanes and then also on other additives. When we look into the properties of the Omocere, they are a little bit in between silicone, pure inorganic materials, and pure organic polymers. Also in the layer thickness, so the typical layer thickness for Omocere is between 2 and 5 micrometer. But there's a huge range of properties. So there are bio-Omocere and Omocere materials already also in the market, which are very hard, very brittle, for example, scratch-resistant materials for optical devices. And then on the other side, barrier coatings for paper or also textile coatings. So very flexible, very organic material, and that's all this Omocere. The Omocere process, it is in principle very simple and comparable with classical lacquer formulation. So you have the synthesis at the beginning, a wet chemical synthesis, not special, not complicated. Then we have our lacquer, or we call it sol. It has a certain solid content, and then a water and also an ethanol or alcohol-based ratio. And this lacquer can be applied on the substrates with conventional methods, so dip coating, spraying, roll-to-roll processes, also printing processes. And then we have our wet film on the substrate, and this wet film has to be cured. And curing in this case means evaporation of the water in solvent and also a chemical reaction. So this curing, a temperature curing, a UV curing, causes a chemical reaction and, for example, a network formation, a polymerization. And then we have our final coating layer. We can coat many different substrates, starting from metals to glass, different polymers, also bio-based polymers, cardboards, paper, textiles, also technical textiles, and even natural and artificial leather. The Omocere, due to this toolbox character, can have a lot of different functionalities, and some of them can also be combined. But in general, there are typical functionalities like hydrophobic, easy to clean behavior, a certain gas barrier for example, for packaging application, scratch resistant, a very broad application, but really in the center of a lot of products. Conductive and anti-static behaviors in coatings, decorative coatings where we integrate dyes and pigments. We can integrate also other additives like flame retardant additives. The material is corrosion resistant and can also help to protect metals from the corrosion by acids or also even bases. And we can also integrate antimicrobial additives or make the whole material biodegradable. When we look on this easy to clean, hydrophobic behavior, we can address this by different approaches. I come to that point in detail later, but you can use, for example, fluoropolymers, silicones, long alkyl chain. You can add particles to have this classical lotus effect and equip different materials starting from leather, from glass, from metal, textile, and produce a water repellent property here. Of course, the barrier, and we work together with the Fraunhofer IUV very close, we can integrate the barrier properties into the homosphere due to this very high network density. Due to this inorganic and organic network, we have a barrier towards oxygen and also fragrances, aromas, and equip paper but also polymer-based materials with oxygen barrier. Scratch resistant is very important when you look on a cell phone, for example, a display or camera lens. And with the homosphere coating, we can, for example, equip polycarbonate, PMMA, with a scratch resistant coating. And with such a coating, the surface is comparable with glass, so very hard. And we can equip also aluminium foils and aluminum materials here. And on this picture, you can see on the top side, it's a coated material and you cannot see the scratches from a taper abrasive test. On the bottom, you see clearly the scratches, and also on the PMMA slide, you can see the scratches, and on the bottom, no scratches due to the homosphere layer. And one of the first products was really the scratch resistant coating on optical devices, and this is still in the market and for more than 20 years, and it can really show that the homosphere material can be in the market and can be also successful over several years. Anti-static and conductive material, we can integrate a certain conductiveness by particles or by chemical modification, and in the lower range the coated surface show the anti-static behavior. When we integrate more or other additives, it can be even conductive, even if the normal homosphere, due to the silicate and polymer character, is not conductiveness. The scratches, the anti-corrosion coating, especially for metal surfaces, can protect the surface from acids, from solvents, from agents, from cleaning agents. It can be applied as a top coat, but I would prefer to use the homosphere as the primer. It has a very good adhesion on the metal, and it can have a very good adhesion on the top coat, for example, of a epoxy or polyurethane-based top coat. And so you have a very good connection between different layers, and such materials survive many thousands of hours in the salt spray test. When I come to one special property, the PFAS replacement. PFAS is in the moment in all media and very critical. In nearly all kind of products, PFAS are used, and they are really persistent. So they are called forever chemicals because they stay in the environment forever. They do not degrade, and they are very mobile. So you can find PFAS in the Arctic or even in the milk of mothers, and that is really a problem because it causes also cancer. And especially in the EU, but also in other countries, the PFAS should be replaced by alternatives, by safe alternatives, and the homosphere is probably one candidate to replace it and to be an alternative for these PFAS materials. The PFAS is used because it has a lot of different and a lot of very interesting functionalities. Starting, and we know that variable is this repellent, water repellent, oil repellent property. But we can also, or we also know it from this UV stability, the chemical stability. It has biological stability, it is flame retardant, and has an insulating character. And the PFAS has all of these properties, but it's not really possible to replace the PFAS with one of the material, and all of these properties can not be integrated in one material, in one alternative. So it's important to look what is needed for the product, and probably you have to use different alternatives for different products and different use cases. I will go a little bit through different properties and start with the repellency, and I gave a short introduction here some slides before. So we used in the past this fluorosilane materials, but now we really avoid this, and we found alternatives, especially in some silicone additives, and here we can equip different materials with such coatings. When we look to the Omosare in detail and a little bit of chemistry here on this slide, we have our Omosare backbone, which reacts like described before, and we can, for example, introduce long alkyl chains, for example octyl silanes here, and they are connected covalent bond to the backbone. We can also integrate different silicones of different properties, integrate particles for this lotus effect, and can also use bio-based sugar fatty acid esters, and they can also be biodegradable. So there are different possibilities, different approaches to have this anti-fingerprint, this easy to clean, this hydrophobic character to the Omosare, and each of these approaches has different results and different properties. When we look on paper, one application of PFAS on paper is the packaging of fatty goods, for example burger papers and things like that. And the Omosare can be an alternative here because it is crease resistant, and it gives a certain barrier to the paper, which shows that the crease does not migrate into the paper structure and is stable for more than 4 weeks. We use here silicones as an additive for the Omosare structure, and on the other side very high organic Omosare formulation. So to replace PFAS regarding the crease resistant or the fatty resistance, I would say it's could be a good alternative here. But there are also other use cases in the industry and also in the R&D. For industry, the coating of different molds, for example injection molding or slush molding, is very important because the polymer should not adhere to these molds. And one option is to use the Omosare with a high inorganic ratio, because then it's has a higher stability towards temperature, and again with silicone additives. And here we can reach more than 100 release cycles in comparison to 20 release cycles with the state-of-the-art material. You have really a good improve of the status of the art. Another use case for hydrophobic and also oleophobic coatings is the textile sector. We know that very well. Each outdoor jacket is coated. For example, also shoes are coated. And when we would like to replace PFAS, the main issue is the repellency towards water. And here we have we developed a pure water-based material. So we have no ethanol, no alcohol in the material, in the coating layer. So it's very safe, and we use silicone as an additive. It's not easy to combine this, but these formulations are stable and can be applied on different textiles. And we look on the spray test, so that's a very distinct test to prove water repellency of the materials. We can achieve values between 90 and 100, and 100 is the best value. So we can improve from 50 to 100 and equip really outdoor clothes with such functional coatings. We have also a EU-funded project. It's called 제3회, and here we do not only develop water and hydrophobic materials, it should be also omniphobic. So everything what is on the textile should be repellent, and we try to achieve this by a combined plasma pretreatment and an almost air overcoating with a structuralization also silicone-like materials. It is not very easy to transfer the results from flat, for example, glass or plastic surface to the textile structure, because you have always a 3D effect. But what is possible here is shown on these pictures. You see a normal water droplet, it flats down, so you have really a low contact angle. But with the silicone, also of the particles, you can form contact angles of more than 145 degrees. And you can see on this video you have really droplets that behave like gummy balls, and when you compare it and transfer it to textiles, you can also achieve very high contact angles towards water. And at the moment the task is to improve also the oil repellency for several use cases here, especially for membranes or other textile applications, filtration, things like that. When we look on really hard facts regarding the easy to clean properties or water and oil repellency, classical PFAS materials or fluorosilane, they offer a surface energy of less than 24 millinewton per meter. And the principle for that is the seaweed effect. So this CF chains, they really behave like liquids, and so attaching liquids, attaching dirt doesn't really affect the surface. They only see this liquid chains, and we try to imitate this effect also by silicone chains. And when we look again on the hard facts, on the contact angles, with several formulations of Omocera and a combination of different silicones, we can really achieve quite low values for the surface energy, comparable with that of PFAS. And that means that we have a high contact angle towards water and also towards diode and we even prove different mineral oils for their repellency. Another aspect of PFAS materials are the electrical insulation. They are insulating, and also the Omocera are insulating materials due to this inorganic, so silicate structure and also polymeric structure. Both are not conductive, so the Omocera, especially in different layer thickness and with different add-ons, can have this high voltage and this high chemicals, this high electrical strength. Another aspect, and that is very important, is the chemical stability of the material. PFAS are very stable towards all of the chemicals, and the Omocera itself is stable towards water, ethanol, other solvents, even aromatic solvents, and also different acids. One weak point is the silicate network, and that is the reason why we choose more organic-like formulations when we want to have high chemical stable materials. But even with the Omocera, we can achieve very good results in dishwasher tests and contact tests with media with a high pH value. Then of course the mentioned anti-corrosion formulation, it's also stable towards mineral oils. We cooked Omocera layers in the mineral oil for more than 48 hours at more than 90 degrees, and it's completely stable. So when we summarize that a little bit, the Omocera is stable towards acids, towards solvents, and when it's adjusted and optimized, it can be also an alternative for surfaces that has direct contact to basic materials. Temperature stability, due to this inorganic content and silicate structure, everybody knows very well, glasses are very inert to high temperatures. The Omocera can also have a high stability here. More than 250 degrees is normally not a problem. There are even formulations that are stable up to 300 degrees also for a longer time. and the key here is to have a high inorganic content, to have low molecule chains, and so up to a certain temperature the Omosare can also be here an alternative, but it has double checked how long, what is the heating rate, things like that. When I come to the next topic, biodegradable or bio-based materials, we call them bio-Omosare. Then I would like to come to the bio-Omosare. That's a more sustainable alternative for the Omosare. And when we look on the structure, everything is correct what you also already showed you about the Omosare. So in principle, the same basic information, basic structures, but here we add additional modified biomolecules, and these biomolecules act like breaking points in a network. So the material is not fully bio-based, only a certain ratio is bio-based, from 5 to 35% in that range. But it helps a lot and helps also degradation of the material. It was developed for packaging materials, especially for bio-based polymer films. When you look on the degradation in detail, we tested it with an external laboratory in Italy, and they checked the industrial composting conditions, and what we saw is that after 120 days more than 90% was degraded. And we also tested some home composting conditions. Our institute, we are not the expert for that, but we try to imitate the parameters. And what we saw also here in this example with different saccharide-based coating layers, depending on the molecular weight, we have also very fast degradation rates and can adjust the degradation rate a little bit by using the ratio or by varying the ratio or varying the biomolecule. When you look on the barrier, and also that was the first approach for the bio-Omosare, we can improve the oxygen barrier of polymer film, for example, quite a lot, from more than 1400 to around 340. The initial idea for the bio-Omosare was the application on packaging films to improve the sustainability of the whole barrier stack. That is quite high, and here we saw also the problem of the bio-Omosare. It's not only a mixing in of the biomolecules in the Omosare matrix, it's really a chemical reaction. And when we modify the biomolecules and achieve a chemical bond between the biomolecules and the network structure, we can improve the barrier quite a lot and achieve values of around 25. So that was the initial thoughts, initial approach for the bio-Omosare. In the meantime, we develop further formulations, further application, and one is the use of milk films. So in some areas, it's very common to use such polymer-based milk films, and the problem here is that they stay very dirt on the film, on the fields, on the soil, and they will be mulched, and it generates microplastic. And ideal alternative is paper, because it degrades after a few weeks. But the problem is that the milk paper is not mechanically stable, so you cannot use it as normal milk polymer films. And the idea of this project and what we achieved is that we coat this milk paper with a bio-Omosare, and it helps to stabilize and improve the mechanical stability, but also improve the resistance towards biodegradation. And when we look on a pure paper, after 4 weeks the whole paper was degraded, and when we coated, we achieved around 16 weeks of complete paper, and after that the degradation starts, and that is the whole time for a growing period, and it works quite fine to equip the milk paper with additional functionalities. The second project which I would like to introduce you is the application of bio-Omosare on textiles. One use case is the reinforcement of plastic parts, for example sports goods, automotive parts, automotive models, and we use hemp fibers here, long hemp fibers, and they are coated with bioMOC material to improve the adhesion between the fibers and the epoxy resin outside to produce these modules, and also to regulate the water uptake. The second use case in this project, and where we also use bio-based materials, is the application on artificial leather for automotive but also for home applications. And here we integrated additional self-cleaning properties, easy to clean properties, and of course the coating has to be mechanical and chemical stable. It should be also very flexible, that no cracks, things like become into the coating layer. And we could show that the bioMOC is not only a concept for packaging, it is also a concept for other application in the textile sector. And also over this textile sector, we have also application in the automotive sector, in the consumer goods sector, with the bioMOC. And in another EU project called Impress Me, we developed in 6 different use cases bio-based products equipped with bioMOC, and they bring to the bio-based materials, for example, scratch resistant, UV stability, but also antimicrobial behavior or easy to clean properties. So you can really see the bioMOC concept works also on high value products and can be upscaled up to TRL 8 so far. The last topic of my talk today is silane-based nano and superparticles. It's another group in our institute, also very familiar with the chemistry. So they have the material development part, they have the processing part, and also the application. And when we look on the material development, they use wet chemical production processes to produce the particles. They make also surface modifications of the material, produce pure salt shell formulations, and of course characterize the materials. They can produce particles with different shapes, so rod-like shapes, round shapes, many different sizes, from some nanometers, 3, 4, 5 nanometers up to several micrometers. And the special thing, and I come to that point later, is also the amount of material. They can really produce several kilograms of the material, which is quite a lot for nanoparticles. And that shows the possibility to upscale such processes also in some pilot plants. Surface modification is sometimes very important to bring additional functionalities, for example, sensoring, also some adhesion properties, also to integrate biomolecules, cells, things like that. And it also helps to disperse the material, to stabilize suspensions with these nanoparticles. So surface functionality is very important, and you can equip this with standard formulation, but also with Fraunhofer ISC formulation, and overcoat each of this particle. And a special thing is that you have really a very, very high surface area, and for some processes it's very important. Here are some characterization methods shown. I would say a lot of things are not very special and very common in many laboratories or research institutes, or also in the industry. We have, for example, a special SEM, scanning electronic microscope, where we have a micro lab in the SEM, so we can do pressure measurements or measure the conductivity between different particles, and that is very special in our institute. When we look on the processing, we have the spray drying process, and I would say that stands in the center of this group, and also in the topic of special nano and superparticles. With the spray drying process, which is a process which is easy scalable, and you can produce a lot of material with this process, you can really tailor-made superparticles. We call them superparticles because they are built of several nano or microparticles, and it can really produce tailor-made materials. you can combine different functionalities in one particle. You can modify the surface, you can adjust the particle size, the particle shape very well. And that is a great tool to provide tailor-made materials. One other process is the inductive heating. It's iron oxide based material which can be also surface modified, and with induction equipment you can heat up these particles very quick, more than 1500 Kelvin per second, and they are particles. They can disperse in a liquid, also in polymers, in solid materials, and depending on the ratio, also on the kind of particles, the heating range and things like that can be adjusted very well. And the idea for that is that it helps to recycle materials. You can also integrate a bonding, debonding of the materials, and of course a sensoring. And it's shown here on this slide that you can combine this functional nanoparticles with epoxy resin and a hardener, and it's well dispersed in this polymer. And on the film you can see that it's heated up to a certain temperature by the induction, and then the polymer melts or degrades, and this helps to solve the bonding between the both components. The particle-based coatings are another approach. I showed you a lot about the Omocere. The Omocere are hybrid materials, so inorganic, organic coatings, and these materials are only inorganic coatings, so they only have the salt shell technology approach, and we produce here very porous material, and they can be used as anti-reflective coating, electronic coatings. But they can also be used as a sensoring material because they have a very high surface energy, and this helps to react very direct and without any time or loss of sensitivity. We produce also larger particles, so in a micro scale, and we use here a certain kind of encapsulation, special nozzle. Two materials can be integrated in this nozzle, a core and a shell material. The shell material is a special acrylic lacquer, and this nozzle vibrates very quick, and so droplets are formed, and in brief the core can be a salt hydrate, a phase change materials, but also nearly all kind of liquids. And by this vibrating, the droplets are formed, fall through a UV curing chamber, and it's ready. And so we can produce particles from around 1 to around 5 millimeters, from 1 micrometer to about 5 millimeters. Mentioned it a little bit, but one competence of our institute is also the upscaling of material. We have the possibility and the equipment to upscale, for example, the synthesis. We have several 100-liter reactors to produce lacquers, for example, or nanoparticles in the 100 kilograms scale. And when we look on the Omocere, 100 kilogram are enough to coat around 10,000 square meters of material, so we can really coat a lot of substrates and test a lot in the pilot phase. We have spray drying equipment which can produce several kilograms of the nanoparticles. Also the encapsulation machine is a pilot scale machine, and the centrifugation is semi-continuous centrifugation, so we can really produce in a semi-continuous process several kilogram, even around 100 kilogram per day. And then the applications, of course, these nanoparticles has a lot of application. I selected several of them and would like to start with catalysis. Due to the structure, we have a very high surface area, and that helps to improve and accelerate reactions. For example, a sunlight introduced production of chemical fuels, but also artificial photosynthesis or the generation of special chemistry or chemicals out of propane. and that is very effective, and the catalysts are produced in a large scale, and you only need some grams for this production, so it's also very effective. Sensoring plays an important role, and here we need this particle base because of this porosity structure to integrate the particles. The particles are functionalized with a special dye which is sensitive towards hydrogen, for example, and with a small contact of hydrogen the color changes. This is reversible, but when the hydrogen works longer time and the duration is longer on these particles, it's not reversible. So you can really have a sensoring for a short contact and also for a longer contact. And the application here is, for example, on tubes, on fan tiles, but also on special safety equipment. And we are improving at the moment the quality, the sensitivity, and also the upscaling of the material. A well-established idea is the removing and recovering of materials out from wastewater, and we have the approach to use magnetic particles. These magnetic particles, they act like a carrier, so they are stable in the water because they are very, very small, but the surface is modified, and for example phosphates, toxic metals can adhere on this functionalized surface. Then by a magnet you can remove these particles from the water, from the wastewater, and clean it, and then you can recover the magnetic particles. Then you have the magnetic particles again as a pure material and can reuse it, and on the other side you have this recovered toxic materials or phosphate from the wastewater. And here you can see the nanoparticles, which is probably a very special thing, can also be integrated in a large-scale process like the cleaning of wastewater, for example, also in hospitals, to remove medicines from the water. And then the nano additives or the additives, so all of this functionalized materials, particles, can integrate in coatings and polymers. And one additional application, one additional material are the LDH, layered double hydroxides. These are special clays, and we produce them that the particle size is really in a nanometer scale. So we can integrate these particles in the homosphere structure, for example. The homosphere layer is quite thin, around this 3 to 5 micrometer, and then you integrate this layers or this LDH in the homosphere layer. You have no additional surface roughness, but it's very effective to reduce the production of steam and reduce also the tendency for flame, so it's a flame retardant material. And I would like to thank you for your attention. This work is done by our groups and also by the group of Benedikt Schuck. He is the head of the particle technology in our institute, and I'm looking forward to questions and for discussion.